All right, everyone out there, it's come to my attention that a lot of coders out there, due to coronavirus, have been sitting at home. They haven't been flexing their coding muscles, and they're getting weak and flabby. And this is not what we need. Come summertime, you're going to have to be out there on the code beaches, rocking that code body. And so what we need to do is we need to get back to work. I'm talking about focusing on the basics. I'm talking about Codelesthenics. And we're going to get started right now. We're going to do a quick 25-minute code workout to get you back in the groove and get you feeling those code muscles every day. Let's get started right now. There we go. Start with a little warm-up. Just get in the groove psychologically. Start thinking about statements. All right, now the first thing I want you to do, just open up your editor. Just get in the groove. Let's start with a little include. We're going to bring in the C standard library. I'm talking about standard.io.h. And now we're going to need a main. No arguments this time. No arguments. I don't want to see any void mains out there. That is non-standard. That's something that MSVC will accept, but is non-standard. I want to see you returning that 0. The command line needs it. It needs to set the error level. Okay, now I just want you to think about a file on your hard drive. Something with some text files in it. We're just going to open up that file, okay? We're going to go ahead and say file star, and we're going to open up a file on your hard drive. And you can put it right in here, whatever file you want. Again, this is just warm-up. I don't want you to think about taking command line parameters. I don't want you to think about anything of that. Just find a file on your hard drive. I'm going to go over here. I'm going to look in what's in the wtemp directory. I'm going to go ahead and load up standardpingtest.cpp. All right. We're going to put the full path in there. And then we're going to check that handle. Again, just a really light warm-up. Just check the handle. And if we don't have that handle, what are we going to do? I don't want to see you just nerfing that else statement. I want to see you passing standard error. I want to see you printing out an error message. There we go. All right, now just take a deep breath. I want to see you focus on your breathing. Focus on getting those lines in. All right, now what are we going to do inside the file? What are we going to do before we do anything else? We're going to close that file. All right, I don't want to see any dangling file pointers. Don't want to see any dangling file pointers this entire time. All right, save that file out. I want you to switch over to your command shell and go ahead and do a build. Check for those errors. If you've got it in your editor, you can do a build right there if you want to. Now let's pop over to the debugger. Let's make sure we can step in. Make sure you got it set up so you can step in. I want to see a lot of debugger use on this stream. I don't want to see anyone assuming they know what's going on in their code, okay? You don't know what's going on in your code till you step through it in the debugger. I said it once, I said it a million times. I've seen too many people in this gym, they don't step through, they think they're done, they haven't finished their workout. All right, go ahead and exit out of that. All right, and now we're just going to kick it up a little bit. We're going to start taking that file from the command line, okay? We're going to take that file from the command line. We're going to say, all right, argc, argv, go ahead and bring those in. And we're going to go ahead and check to make sure that we've gotten an argument, all right? We're going to go ahead and make sure that we've got our argument greater than 1, okay? And if you want to here, you can check for greater than 1 and be permissive. If you'd rather be specific, you can check for exactly 2. Again, what's that first argument? First argument is the executable. It's not the file we're loading, it's the executable. All right, so let's go ahead and pull out that file name here. Again, just really gently. I don't want to see any injuries out there. Just go ahead and grab that argv, no bugs. And now we're going to open up that specific file name. Okay? Things are starting to get a little more real now. I want you to be able to print out which file is not being opened. Don't leave that user hanging, okay? Go ahead and kick a %s in there and print out that file name. Whatever can't be loaded, we want to let them know. All right. Now, what happens if we don't have enough arguments? We don't just dump the command line, okay? We print out a usage line. And what's the best way to print out a usage line? That's right. Use that executable we already got passed. So we're going to go ahead and say, look, we need you to tell us what file name to open. All right, now what are we going to do now? Are we just going to assume this is right? Absolutely not. First, check for errors in that build. I don't want to see any errors out there. I don't want to see any warnings either, okay? No warnings, no errors. That's code muscles. All right, now let's go ahead and double check that everything's working properly. We're going to go to that build. We're going to go to our codeless.exe, and we're going to see what happens when we hit return. Again, there's that usage line. That's what we're looking for. Now we're going to go ahead and see what happens when we pass a file name. Let's go ahead and say foo.cpp. Can't open it because it's not there. Finally, let's do our last check. Going to open up that STB test file that I was talking about before. Again, now it works. All right, now we're in good shape. You can feel it start to kick in. You can feel that blood pumping. This is when we start to flex our code muscles, okay? What are we going to do now? We're going to go ahead and read in that entire file. That's right, we're going to read in the entire file, the whole thing. That means we're going to go ahead and pull in. We're going to put in a little malloc here. We're going to be able to start allocating some memory. We want to know where our stuff is going, okay? I don't want to see any boost. I don't want to see any of this. I don't want to see any STD going on in any of this thing here. What do I say? No STDs. Never give STDs to your friends. Never get STDs yourself. You want to keep STDs out of that code base. Keep it clean. Okay. Here we go. We've got our file open. We're going to want to f-read into this file, the whole thing, but we got to find out how big it is first. How do we find out how big it is? That's right. We use an ftell, okay? We're going to have to see how big that file is. We're going to need an fseek and an ftell, so let's go ahead and fseek to the end of the file. We'll do an ftell, and then we'll fseek back to the beginning, all right? Ready? In 5, 4, 3, 2, and 1. Go ahead and put that file pointer in there. And where are we going to go? We're going to go no offset, and we're going to go seek from the end of the file, right? So we get to right to the end of that file, and then we know to pouch back to the beginning. We're going to do the same exact thing, but we're going to be able to seek from the position of the file, okay? Now go ahead and check those errors. Make sure that you don't actually get any ones there. There you go. See, that seek was an error. That was exactly what I'm talking about. I'm getting flabby too. Sitting home with coronavirus, I've got the wrong actual seek in there. How do we figure out what the seek is? Okay, there's a couple ways we could do it. We could open up the actual file. We could look for the documentation. But what I'm going to go ahead and do is I'm going to go the hard route. We're going to do the hard route here on Code Muscles, and I'm going to go ahead and search for that file. So let's go ahead and bring up wherever the SDK is. I know this might take a while, but it's worth it. When you get those big gains, it's going to be worth it. Knowing where the SDK is, go ahead and find it on your machine. It's going to be one of two places, program files or x86. Let's go down there to the SDKs, Microsoft SDKs. There we go. And here we got our Windows and Windows kits. I'm going to go ahead and search in there first just to make sure. There you go, doing that search. No items match your search. All right, let's check in the same location over here. Under program files. Working on it. Still no items match our search. All right, I don't know where this actually went on this machine. Looks a little bit weird. I'm going to go ahead and switch over to Findstir. I'll tell you, this is a little bit weird. I kind of don't know exactly what's going on over here with search program files. Even if I search the whole drive, you're telling me you can't find standard.io.h? Maybe Microsoft's the one that's getting a little flabby. Interesting, we can find the boost one here in VoiceBridge. Microsoft taking a sweet time there. Alright, what the heck. I figure if it can't tell me where it is, someone can. Even this can't tell me where the file is? I don't think I've ever seen that before. Usually you can find out exactly where the file is from somebody. It's like this file doesn't even exist on my machine. How is it possible? I have absolutely no idea. I promise you eventually someone will know where this file is. It just doesn't look like anyone on this machine actually can find this file. I guess it's been hidden somehow. I have absolutely no idea how. It doesn't even show up in internal dependencies. Oh, because this is a text file. How did it create a text file for me? Let me go ahead and create a real file. There we go. Beautiful. So here we go. We've got seek cur, we've got seek end, and we've got seek set. That's a 0 there. Probably should have just remembered to pass 0, honestly. If we were really flexing our code muscles, we probably wouldn't use those identifiers. But I'm going to go ahead and use it anyway. Who knows why this couldn't be found? If we go ahead and take a look at where this file is, by the way, it should have been found in that actual dependency. You can see when we take a look at where this file actually exists, the fun file that we're actually in, if we look at where it exists, it should have been found by that seek. I don't know what's going on there. If we come in here and we actually check out open containing folder, you can see here it was exactly where we searched. So who knows what's going on with Windows? It apparently can't find files that it already knows where they are. Maybe we just didn't let it complete. Oh, yeah. It was just too slow. It's still not done looking in that directory. All right, so it would have found it eventually. We'll let Microsoft off the hook on that one. It's not their fault. There's too many files in the program files directory, I guess. All right, let's finish up. We're going to go ahead and do an fdel here. We're going to find out where our file actually is at this point in time. And we're going to go ahead and figure out what that actually takes as well. So we can go ahead and open that file too if we need to, if we want to actually look at the definition of fdel, but we don't actually need to at the moment because we'll be fine with just small files at this point. All right, we're going to go ahead and use an int for now for fdel, and if this happens to be a 64-bit build, it should tell us if it doesn't want to actually return that. So let's go ahead and do end of file here, and we're just going to load. That'll load at maximum 2 gigabytes. It will not load any more than that. I could go ahead and do an int unsign here just to make sure that we don't get any wrapping, and that's just good code behavior. So I'm going to go ahead and do my fread now, and I know that this is going to be the size of the file that we're actually reading in, and I'm going to go ahead and take that file there. Now remember, for whatever reason, fread decided to take 2 different parameters. It tends to take both the size you want to read and the count of things you want to read. In this case, we're not really going to use both those parameters. So I'm just going to put an end of file and a 1 in there. So let's go ahead and finish up our fread. We've got our file, and now we're going to have to use a buffer here. Now, we don't actually have the buffer, but if we build, we should see that's the only thing left that we haven't done. Okay, so here we go. We're going to go ahead and create our buffer. We know that our buffer needs to be exactly as big as our fdel told us. So maybe let's go ahead and change this to file size. And then let's go ahead and allocate our buffer right here. We're going to do a malloc of the file size. And we can do this as a char star or we can do this as a void, either one. I know we're going to want to use this as a char star, so we're going to go ahead and allocate it as a char star. Now, we don't actually know if we can get the memory back. It's very unlikely that we wouldn't be able to, but we're going to want to make sure we don't use that buffer until we actually have it. So I want you to go ahead and add another error message in there really quick. Just tell the user, error cannot allocate space for buffer. All right. Finally, we have our file in here. Let's go ahead and build. Let's go ahead and see what this is returning. All right, so we are in a 64-bit build potentially, and our fdel is going to return a size T. That's great. That means we can handle bigger files if we want to. So let's go and change that file size to a size T. And then let's go ahead and change the fread to make sure it's getting the parameters we expect. Oh, these are in the opposite order. So let's go ahead and put the buffer first, file last, and build. So now we should be reading the entire file in, and we can verify that if we want to. Now, if this was a large file that you picked, you probably don't want to do this, but we can go ahead and do an fprintf just to make sure we actually have the entire file that we think we have, and I could test that out now. So if I come back here and I do a build and I do a run, you can see that we're going to go ahead and print out any file that we actually have in there. So I'm going to go ahead and use that same std pingtest.cpp, and there it is. All right. Now, we've got some garbage at the end. Why is that? That's because this is not going to be null terminated. This %s is going to print out as much as we have here. Now, we have 2 choices. We can either print our printf with a size, or we can go ahead and null terminate at the end of this. I'm going to choose to null terminate at the end of this so that we know we can pass it to anything and we won't get any bugs. I don't want any hidden bugs in here. I don't want to see you putting any hidden bugs in here. So let's go ahead into the file size here and make sure we get 1 extra slot for our null terminator, and then we're going to our buffer. We're going to put into the end. We're going to slap that null terminator in there. Just put it straight on in there. So let's go ahead and do that build. We're going to go ahead and do our run again, and now we should see no garbage at the end, right? I don't want to see any of that in there. So here's that file. We know we're reading it correctly, and now if we want to, we can start parsing it out. And what I want to do here is I want to get into the fundamentals, all right? We've got something. Let's go ahead and make a linked list of all the lines in this file, all right? So I want to see you creating a structure. I don't want to see any classes, none of the C++ nonsense. I don't want to see anything virtual. I want to see actual code that a CPU can execute. None of this strip crap. All right, we're going to go into that struct. We're going to create a link, and then we're going to create a list so that we've got both of them. We're going to go ahead and put in a next pointer into our list, and we're also going to go ahead and put in a string. Now, I don't like to use null terminated strings very much. I like length strings myself. If you want to use null terminated, that's okay, but it's going to be a little bit more difficult for you. You're going to have to do a little bit of extra work. But I'm going to go ahead and create my own string here, and I'm going to say that my string has the size of the string and then the data for the string. And that way, I can just pull out pieces of strings and use substrings, and I don't have to worry about constantly inserting null terminators. That's just going to save me a lot of work going forwards. Now here we are at the link. We know we got to have a string for whatever the line in this file is, and then we're going to have a list. The list is going to have the first and the last thing because I want to be able to append to this list. So this is a singly linked list. It's got a first and a last pointer, and each link contains a line of the file. All right. Now how are we going to do this? Well, we got to go through we've got to go ahead and take our buffer, and for each line of the buffer, we're going to create a new link. And here's the thing. If I'm going to go ahead and do this malloc, we're doing a linked list here. We want to be friendly to the cache. So I'm going to allocate in batches. I don't want to see you allocating links from all over the memory space and missing that cache every time I go to get another link. I want to see you putting all of those links right next to each other so our linked list has basically the performance of an array. Right? That's what I want to see. I don't want to see any of these scatters. Scatters are no good. You know that the CPU can't find those scatters. So let's go ahead and make our link allocator now. We're going to go ahead and make a link here. I want to see some statics in here. I want to make sure that you're not putting extra pressure on the linker. So you put that static in there, take it out of the link line. Take it out of the link line. That's how you get that fast compile performance. All right, so we're going to go ahead and have an allocate link here. And when we allocate link, we know we're going to want to have a memory pool, all right? I want to make sure that we have that memory pool available, and you can do this one of two ways. If you're looking for future proofing, you can actually pass a memory pool in here. So this is Codelesthenics, that's the way we're going to do it. If you want to do a global variable, that's also okay. So here's our memory pool. And in this case, I'm going to go ahead and say this can just be a link pool. And that has our first free link, just so we know we can get a free link if we need to, and then it's also going to have essentially a push buffer, okay? And we can do this in two different ways, actually. We can do a first free link, or if we want to, we can just go ahead and say that it doesn't work that way, and we put all the things in the free list at the outset. Maybe I'll do it that way for starters. There's other ways you could do it. So here you're going to pass that link pool, and you're going to tell it to allocate a link. There's no other information that you actually need for just allocating a link. So what's that going to do? Well, it's going to produce a result. It's going to say, look, whatever the pool's first free link is, that's what our link is going to be. And then what we need to do is we need to advance that first free link pointer. But we might come to the end of the pool. And if we're coming to the end of the pool, we got to allocate a new pool, right? And that's going to inform our design of that link pool structure. So we're going to go ahead and say, look, if the result is positive, we got a result back, we actually got a link, we're going to go ahead and return that link so we can advance the pointer. If not, we're going to have to actually put in a value there. Now, either way, I'm going to return that result so that the user gets back the link we talked about. We're going to go ahead and check the result here. And if we did get a result back, our first free link is going to have to be equal to the next thing in the free chain. If we didn't get a result back, that means there's nothing left in this pool. So we're going to have to go ahead and allocate another link pool. Now to do that, what I could do is just say, all right, there's going to be a link pool addition here, so we can go ahead and chain those link pools together, just so we can keep track of all the links we've allocated. Now again, we're probably not going to actually need that, but it's just good code hygiene, because we know we might need that in case we want to free all the link pools together. So in the case where we can't actually do that, what I want to be able to do is push this link pool down, essentially go ahead and create another link pool and keep moving things along. So in this case, what we're going to do is we're going to allocate a link pool here. We're going to say, all right, we've got a new pool. Let's go ahead and malloc the size of a link pool. And of course, we're going to have to go ahead and cast that. I don't want to see anyone calling new. No strip in this code base. All right, we got to make sure we get it. If we don't get it, this is a fatal error because this program can't actually do anything if it can't process all the lines of the file. So that's just going to be a standard error. And in that case, we can also exit with an error code. But that's basically the only condition we actually have where we're going to have an error. Now, there's two things we could do here for the link pool. We could actually allocate this plus the number of strings we want. And as far as I'm concerned, that seems like a better plan anyway. So let's go ahead and say we'll do a certain number of strings at a time. So in this case, for each individual link that we're going to allocate, I'm going to go ahead and say we've got a link count here, or links per pool might be a better name for it. And I'm going to say how many of those we've got. All right, let's go ahead and say we do at least, 4,096 links per pool, because anything less would not be very muscular. So in here, we're going to say, look, we've got links per pool times the size of a link. That way, we're going to allocate everything in one big flat chunk. Again, friendly for the cache, friendly for you. Everything gets allocated in one go, no additional error checking. It can also be freed in one go, very efficient, all right? None of this piecemeal, allocating links every time, scattering around, thrashing the cache, ruining the layout of the data of the whole program. All right, so if we get that new pool back, we know we have a certain number of links we have to initialize. So we can go ahead and set a link index here, and we can just run through them really quickly. Now, this may be a bad idea in certain arenas where you know you're not going to be using the links that often, so I wouldn't recommend doing this every time. But for our case, we know we're going to use all the links right up front, so this seems like a reasonable trade-off. So what we need to do here is we need to say, all right, that new pool, it's got to be able to take the pointer to the first link. Where's that first link going to be? Well, we know it's going to come right after the link pool structure, right? Right after this is the link we actually have. So we can go ahead and cast that to the link, and now we can step through each of those individual links we have. How many links do we have? We know we have links per pool worth of them. So we know the new pool has to point to the first link. That's a definite. So the first free link in the system, in this case, is going to be that first link, that one right after the new pool, right? So now let's keep going. For each link of the link index, what we want to be able to do here is initialize that link. So we know that these links are just going to go in order, so we can actually just increment the link pointer each time. So every time we can basically say, look, the next link, the one that comes after this one, is just immediately after it in memory. Again, tightly packed, good for the cache, good for you. So here we go. On the last link per pool, we don't actually want to go to the very last one because that one can't have its pointer set for obvious reasons. Although we could do this a little bit backwards if we want to. We could actually do a prev-link situation, and that might be a better way to write this. In fact, you could think of it a little bit more like working like this, where we start with that first link. And let me show you how to do that, because that might be actually a little cleaner, and so you may not have thought of it doing that. So here we go. We're going to take this link here. We're going to call that actually prev-link. And then in this case, we're going to set this first free link equal to prev-link. And then on every one, we're going to set prev-link equal to link plus 1. Okay? You see we're doing that? We're basically saying, look, the next link, the one that we're actually not looking at quite yet, that's the one that we're going to point to, right? And so here we go. Link, next link, equals link plus 1. And then our prev-link equals next link, right? So each time we go, we get it. In fact, we could actually call this link now since we called the other one prev-link. And so now the link's next pointer is going to be 0 in this case. And it's a little bit redundant because you don't actually need to do that. But again, just want to make sure we're clear on each one. Maybe we'll pull it out at the end just for good measure. But the next one is going to be pointing to us. So we go through each one of the links in the pool here, and we pull out which link we're actually pointing to, and then we get to the end. This will actually set that last pointer for us. And again, maybe you think that's a little bit wasteful. If you do, you can pull it actually out, because we have the ability to actually access directly off of each link. And in fact, another way we could do this if we wanted to is we could just access off of the free link pointer. You could do it like this. Maybe this is an even better way to do it now that I think about it. If we set our first free link pointer, we now know exactly where that is, and each one of these can just set up the links for us. We could just say, look, the first free link, links per pool minus 1. We know that one's going to point to nothing, right? So in this case, we know that its next pointer doesn't actually point anywhere, like so. However, when we actually point for each of these, we can say, all right, for every one of these first free links, we know that if we just take a look at the link index one of these, and we can do this again with 0 through links per pool or 0 through links per pool minus 1, so we know which ones we're actually looking at. We can just say for this particular link index that we're on, the next pointer points to whichever one is the next one in the list. And again, this just changed them in order so that they walk linearly through memory, right? And so we do that for each one up until the very last one, and then the very last one just gets a null next pointer. Again, that initializes the whole pool. Each link is right next to each other, so again, streams through the cache very cleanly, even though we're using a linked list. All right, so let's go ahead and take that allocate link. We know that the link pool now is the pool that we're going to want to use. The problem is this link pool handle is something that everyone else is probably using. So what are we going to do? We're going to go ahead and return this link pool as if it was the old link pool, just by romping over it in place. Okay, that's what we're going to do. So watch what we do here. We're basically saying, all right, the pool that we got passed in its next pool is going to be this new pool handle that we got, and then we're just going to go ahead and swap those pointers around. All right, we're just going to go ahead and swap them around so that we don't have to worry about chasing that pointer every time. So here we go. We're just going to say, all right, we're going to take that temporary variable. We're going to go ahead and take that new pool, and we're going to take its first free link. We're then going to overwrite that one with the one from this one, which actually we know is 0, so we don't even have to really do it. If you think about it, if we wanted to actually do this allocation in ahead of time, we would have to do it. Now I think about it, since we know we're already in the 0 case, we don't really have to worry about it. So really we can just stuff that in here and store the link pool separately. Or if we know we don't actually want to free them, I suppose, we can just chain these on. We don't even really need to allocate a new pool. If we want to do it that way, we can do it this way as well. So we can just go ahead and say, look, our new links pointer is just going to be whatever the malloc size of is. Did my music stop? Music does not stop. There we go. So all we want to do here is just say, all right, if we want to, our new links, we can go ahead and malloc those. Links per pool comes out like so. Just cast it to the link. And then we chain those together. No need to allocate a new pool if you don't want to. Totally works for me. Any way you want to do this is fine. All those methods, totally acceptable, as long as you've got them under control. All right, so we don't need to allocate this particularly. We could just use new links directly. So in this case, we can just say, all right, here we go. New links, link index equals new links, link index minus 1, or plus 1. There we go. And we still have to do that last one just to make sure that the chain is valid. Once we have those links, we can just set it to the pool we've actually got. So our pool next free link in this case, or first free link I should say, is just going to be equal to whatever that new links pointer is. And that's all we actually needed. Right? All right, again, allocated, ready to go. We can also move this up one if we want to and avoid the redundant if. We can say this is always true now for the most part. Oh, sorry. We could say this was always true now because we know we exit. So in this case, we don't have to do the result check here. What we can do is just say, all right, instead, we'll go ahead and do this assignment only at the bottom, like so. And then what we're going to do is we're just going to assume we always get it because we exited if we couldn't get the memory. So up here, we'll just check our pool, first free link. We'll allocate if we don't have them. And then we'll go ahead and return the first one always. And we'll always pop that one off because we know we've exited here if we couldn't get any new links. So once we've got allocated link, we're ready to start pulling these out. Let's go ahead and do a for I loop. First, let's check our errors. Go ahead and make sure that we don't have any here. Oop, didn't put a count variable in there. Let's go ahead and check out, make sure our new pool is out of there. We're not using that anymore. There we go. Now our link index in this case, that all looks fine. Just got to finish our for statement. And then down here, looks like we've got a address of and dot. There we go. So now I think we're in good shape. We've got our allocator ready. Let's go ahead and test it out. Let's make sure it's working like we think it is. So we want to be able to call allocate link here. We want to be able to call it in a for loop, like so. And we want to just be able to keep allocating links, right? And we want to do this until we get to the end of the file. Now, I'm going to go ahead and just run through a few of these just as a test. So this is just going to be a basic index. We're going to go through about 64 of these, like so. We're going to allocate our link, like this. And we're just going to make sure that our allocator works. We're going to step through it, make sure it works. Now, we need a link pool here. And in this case, we know we can initialize it to nothing and just have it work, right? Because we know that our allocator will take care of the rest. So here's our link pool. We're going to initialize it to nothing. We're going to go ahead and pass that pool in, like so. And now we're just going to see, when we step through it, the debugger, does it work? Do we have any bugs in here? I don't want to see anyone assuming that this actually works. All right, so let's go ahead in our debugger. We're going to set which file to load. We use the same one that I was using before, just to make sure there's no surprises between what we're looking at in the debugger and what we're running on the command line. So let's go ahead and grab that, put it in here in the command line arguments. That's the file we're reading. Let's go ahead and step in. There's us validating that argument. We're opening the file, taking a look at the size of the file. Let's take a look at how big that file actually is. Just make sure that makes sense, right? And here's the problem here. One thing we don't want to do is this R. I'm worried about that because in this case, we don't really want that line translation. That line translation is going to screw us up because we don't really want C messing with us. So I'm going to pop a B in there just to make sure that we always have the exact contents of the file. Even if it's not a text file, what we're going to do is more or less only going to be relevant for text files if we're looking for lines, but that's okay. I don't want it changing my file size, and I'm going to handle the line endings myself. I don't really want to trust the C standard library to do that for me. So let's go ahead and do a step in here. I'm going to look in what we're doing. I'm going to go ahead and check out that fread. I want to see the file size. Oh, it looks like we're compiling in release mode here. Is that accurate? I don't actually know if that's true. I'm going to slap a ZI into my build just so I can have an easier time inspecting it. So here we go. It looks like there's an O2 in there. I'm going to go ahead and slap an OD in there. And again, that's just to make sure that I can see what's going on. All right, so here's me stepping in. Here's us in the OD. We're going to go ahead and pull out that file size, 581. Let's see if that makes sense. Let's just double check it against what the file system reports. So I'm going to go ahead and say, look, give me that STB file, ping test there, 581. That's the right number of bytes. We're going to go ahead and read that in. Now, assuming we have that read in, we don't really need to print it out anymore. I can get rid of that line. But each individual link that we go through, we want to make sure that that works now. So let's double check that part of the code. And I'm going to delete that fprintf. We don't need that clogging up our buffer anymore, clogging up our output buffer. All right, come set a breakpoint here. We're going to walk through that allocation and just see how it looks. Links per pool 4096. We've allocated those out. We've got new links now. Let's take a look at what that looks like. Here's our memory pointer. And links per pool, again, 4096. So let's see how many we're going through. Links per pool -1. Let's see if we can check to see if the chain that we think should be there actually is there as we run through it. I'm going to pull out a few of these array members here for each of the links, like so. And we're just going to look to see if the next pointers point correctly to each other as we run through. Now, at this point, they should all be basically garbage. And of course, I can't see the actual address of this. So I'm going to go ahead and take the address of that by just saying, all right, new links 0, where is that? New links 1, where is that? New links 2, where is that? So now if I take a look at what we're going to point the pool to, we know that it should be this one. And if we look at what 0 should point to, it should be this one, and so on. So let's see what happens when we do our address of here. I want to see this new links 1, this 1B404C1FC8. I want to see that coming up on the next line, and nothing else will do. All right, there we go. Let's do it one more time. FE0, looks like that's initializing properly. Let's check that last one. All right, I don't want to see any off by 1 errors. I don't want those off by 1 errors sneaking in here. We know that the 4095th element, that should have a zeroed next pointer right here. Let's go ahead and take a look. It looks like it already did, but just to make sure, links per pool -1 is 4095. That should have zeroed this. Now let's make sure we assign the right one here and pop the right one off. If we take a look at the result that should be here, we should be seeing that FB0, that first new links, and that's exactly what we're seeing. And we should be leaving our pool with a first free link that's exactly that new links 1, and it is. So that's exactly what we want, looking like we're in good shape. Okay, so we've got our linked list popping off. What I want to do now is start running through that file. So instead of index 0 to 64, I just want to do a for I loop that will run until we hit the end of the file. So we're going right to the end of the buffer here. We're going to keep going, keep going, keep going. So let's go ahead and start our size T. Let's figure out where we're at. We're going to be at 0 for now, and we're going to keep going until our at runs right up against that file size, okay? Again, this is why I'm saying if it's a binary file, that's okay. I'm not even going to be looking for zeros. We can actually take this out if we want to. In fact, we can go ahead and even do this so that our buffer doesn't actually have any extra space in it, because we're not going to be using that. We're not going to be looking for that anymore. So each time we go through the at, we're just going to look and we're going to see if we've hit a new line. If we've hit a new line, we're going to do some special processing. Now I'm going to do something a little bit different here because I want to handle all different kinds of line endings. I want to handle /r, /n, and /rn all together. So I want to make sure no matter what combination of new lines we're in there, we've actually got them handled correctly. So what I'm going to do is I'm going to pull out those two characters that we're on. And in this case, we're always going to be searching to make sure we want to double check too that we don't have a file size overrun. So what I want to do is basically take a C0 and a C1, and these are going to be pieces of the file system. And so in this case, what I want to do is say, all right, that C0 I know I can always get. It's just going to be whatever my buffer is wherever I'm at. Okay, that's my C0. That's the first character I'm looking at. at. Now my C1 in this case, I don't know if I've actually got it. I have to check first to see if at plus 1 would be less than the file size still. If it's not less than the file size, I can't actually initialize this variable, so I have to double check because I'm using an at plus 1 in here. I don't want to overrun that file. Now again, if we want to, we could use the trick we used before, and maybe that's a better trick because again, these are two different ways you could skin this horse. It depends on whether you care about that extra plus 1. If you don't care about the extra plus 1, you can do that pad, and then in here we can actually do this and say, all right, we're going to get out two different variables. I'm going to leave it this way with the C0 and the C1 just so you can choose which one. I don't want to pre-bias your judgment whether you care about that extra byte of alloc or whether you care about that extra if statement that almost never triggers. In one case, it's basically a perfectly predicted branch. In the other case, it's just an extra allocation, 1 byte over what you're previously going to allocate. So I'm going to go ahead and leave it like this. We're going to grab each of these out here, and then we're going to go ahead and check to see if we've got a new line and which kind of new line we actually have. So first I want to check for the two paired new lines. I want to say if C0 is R0 and in this case if C1 is \n. So I want to look for both of these kinds, right? And then I also want the equivalent case. I want to basically say or if we have the opposite, so if they were flipped around, like so, okay? I'm just checking for both kinds of line endings here. If either of those two are hit, we've got a double. So in this case, I want to update my at pointer a little bit. And you can choose how you want to do this. If you want to see those ats go forward inside, we can always remove the at statement here, but we have to be careful to make sure that we always increment it. And in that case, this reads a little cleaner because you can see me incrementing over the number I actually read. So it's up to you which one of those two you would rather see. Now, we also have some other cases here. We've got an equivalent case that's if these appear in the opposite order. Oh, wait, I already handled that one. Never mind. So then we've got an equivalent case here that we only handle one of them. And that's just say we'll use our \r. So that's if we didn't see a double, we have to watch out for singles. So let's go ahead and put those else's in there because remember, if we handled a double, we don't want to handle a single because one of the singles would fire in that case. So we check just our C0 to see if we have a \r or a \n. And in those cases, we do want to go ahead and move forward by the 1. So those are our line ending checks. That lets us know whether we've hit a line ending. In all other cases, we have not hit a line ending. And so in that case, we can just go ahead and skip where we're at. Now, anytime we've hit a line ending, we probably want to go ahead and set some kind of a flag to let us know we hit an EOL, okay, in this case. So I'm going to go ahead and set that. Each case in here, when we've hit an EOL, I want to remember that we did that. And if we've hit an EOL, we're going to do our end of string processing, okay? So what I want to do, too, is remember where the line ended. So I'm going to go ahead and say that the EOL was at here so that we can remember where that actually is. Now, there's another way we could do this that's pretty good. Maybe this is a nice way to do it, I don't know, but it kind of creates problems for us. So I'm not actually going to do it, but you can actually try to use this as your actual signal by setting it to something else, right? All right, so we need this to be a size T because the EOL in this case has to be the same size as the at, just to make sure that we don't have any kind of mismatch between the sizes of our variables. Now let's go ahead and here in the hit EOL, what we're going to do is we're going to allocate a link, and we're going to go ahead and set that string. All right, we want to be able to set that string correctly so that in here we know that whatever we were setting this string to here for our particular link, it's going to encapsulate the entire line. So how do we do that? Well, we're going to need a running size T here for the beginning of the line, right? We need our BOL. We've got our AOL. We got to have our BOL. Sorry, our EOL, we got to have our BOL. So in this case, as we run through our at, every time we go ahead and hit end of string, we're going to have to go ahead and reinitialize that BOL. So when we hit the end of string, I'm going to say, all right, whenever we're done with that, wherever we're at right now, that's the beginning of our next string. All right, so do we need to record a line here or not? Well, only if there's content. I'm going to say we're going to skip those blank lines. We're not going to put those into our index. So what we do here is we say, all right, if our BOL is actually less than our EOL, meaning there was some content to the string, we're going to go ahead and allocate a link, and we're going to go ahead and string that link through our set. Okay, so let's go ahead and take our link pool here, and we know that we've got a list. Let's initialize our list here to nothing, right? Just make sure there's nothing, no next pointer, no first pointer, and I'm going to need something to add links to this particular list. So I'm going to go ahead and say add or append. Let's go ahead and call that append. We're going to append a link to our linked list. And we're going to do that like this. We're going to take the list pointer, this is the list we're going to add to, and we're going to take the link that we're going to append. So how do we do that? Well, I'm going to do a one-liner here. All right, this is the advanced version. If you want to do a simpler version, you can go ahead and do it line by line. But I happen to like to do single-line list appends. Again, it just keeps me sharp, it keeps me focused, keeps those code muscles moving. So I know I'm always going to set that last pointer to link, right? We know it's always going to be set to link because no matter what happens, after we append a link, we know the last pointer's got to point to that link, otherwise we didn't append. So what's in the middle here? Well, there's two things we could possibly update. In one case, we have some stuff in the list. If we do have stuff in the list, what do we know we're going to do? Well, we're going to set that next pointer. So whatever the last next is has to point to that link. What's the other case we might have? Well, the other case we might have is that we might have to set the first pointer, okay? And that's there's nothing in there. There's no next pointer to set. So we might be setting list first. What determines which of those? Well, it's whether list last actually existed yet. And there's our one-liner, right? That appends to the list, sets the last pointer, sets the first pointer, sets the next pointer, all in one line. Again, good, clean, simple, does what we need it to do. All right, so there's our append function. We're going to go ahead and use that. In here, we're going to do an append to push this onto our list. So here's our list. There's our link. We've already initialized it to 0 here, so we know that it's correct. And then finally, we're just going to have to go ahead and set that line. We need to put in here where the line actually is. So how do we do that? Well, we know we need to count. How do we get the count? Well, the count's pretty simple. All we need to do is look at the difference between these two things. We know exactly where the beginning is. We know exactly where the end is. We subtract the beginning from the end, and we've got the count. And then in here, we just need to know where it starts. Again, super simple. We've got the data pointer. We know the data pointer is just going to be equal to our buffer plus wherever the line began. That's going to store all our lines. And if we go ahead and step through this in the debugger now, we should be able to see it start to work. So let's go overhead. Now, if you're using Remedy BG, give yourself extra code muscle points. This is a real debugger for serious people. If you're using it in Visual Studio, that's all right. You'll get here someday. So let's go ahead and step in. Let's take a look at what our variables are. A lot of new variables in here. A lot of possibility for bugs. I want to see each of those bugs stomped out. I don't want to see any surprises in here. We're going to take a look at our C0 and our C1. They're coming in here. We can go ahead and cast those if we want to chars. Just take a look at what they look like. Or maybe not. There we go. All right. So this is what's at the beginning of the file. We're going to look at both of these. We haven't hit an end of line, so we're just going to advance to the next pointer. We don't actually have to look in here until we get to something that's actually an end of line. We've gotten to an end of line here. It's 15 in. That seems okay with what we've got, but we can double check that in a little bit. When we actually allocate our link, let's take a look at what our link line ends up being, see if that maps to the correct line. Now again, if you're using Remedy BG, good for you. You can actually put a link line stir in here where we actually say, here's the data for the string, and here's the count of the string, and we can take a look to see if that's correct. Looks really good to me. Again, that count. Let's take a look if it includes a new line. I don't know if it does or if it doesn't. I want to see if it includes that new line or not, or whether there's no new line in it. So if there is a new line in it, what we would see is the link line.data link line.count -1. We would look and see in there what we've actually got. Link.data expression not a pointer. Oops, that's because that's supposed to be line. Sorry about that typo. There we go. So the last thing in there is the colon. That's good. I don't want to see any new lines in there, so now we've got our line. Let's keep going as we append these on. Let's take a look. That's just going through all the lines of the file, putting those into our linked list, and we're good. All right. So let's go ahead and make sure we can now print them out. At the end, let's print out all of the things that we actually had in our list. Here's our link. We're going to go till it hits null. There we go. We're going to go ahead and print this to standard out. And I'm going to go ahead and quote this. Now here's the problem. We can't actually fprint this without giving a length specifier. We've got to tell it how long this thing is. We're going to have to use something like a width specifier. So in here where we've got our link, we need our line count to be specified, because if it doesn't have the line count, it will overrun. We don't put null terminators in here, so we've got to make sure it knows that that's what's going on. This size t is too big for this to print out, looks like. Unfortunately. So you know what? I'm just go ahead and downshift to print care. We could go ahead and try to put this as a 64-bit width, which you actually can do, but I think that might be getting too platform specific. So I'm going to go ahead and just do it with a standard write out. Perhaps we could just do an fputs, for example. And again, we also probably want to make sure we can print out binary. So maybe we'll just do an fputc in here, although I don't really want to have to call it that many times. So we could do an fputs. It's tough to say. I'm not sure. That's also going to want to be... You know what? Here we go. Let's just do an fwrite. If we just do an fwrite, we can tell it exactly how many we want. And that'll get us out of the business of having to worry about length limitations. We handle length limitations properly the entire way through. So, in this case, I feel like we shouldn't chicken out when it comes to the printout. Might as well support 64 bits all the way. Alright, let's go ahead and see how we did. There we go, running it. We might want to put in a new line in there, just so we can see it. So I'll go ahead and do an fputchar. Or we'll go ahead and put that standard out. Actually, I guess this guy can be an fprintf. There we go. We're getting some extras in there. What's going on with that? This is our link first. Link equals link next. That should loop through all of our stuff. You know what we do have to do here? We got to go ahead and get rid of that next pointer. Without that, we could be pointing out to anything. All right, there we go. So let's go ahead and step through our code, just as a cooldown. I think we've got everything in here that we need. We want to make sure there's no hidden bugs in here. So let's go ahead and step into main. And we're going to go through each individual line, taking a look to make sure nothing weird's going on. So here's us opening that file. Again, we're opening it in binary mode, just to make sure we don't want any line translation. We're going to handle the line translation ourselves. Here's that file name. That was the first parameter on the list. Again, we check for handling those parameters correctly. We're going to go ahead and fseek to the end of the file. Check out that file size. Here we go. 581. We're going to go ahead and allocate our buffer. We're adding a little bit of extra space. That extra space is not actually for a null terminator, although we did put it in there, just so we can go ahead and check our C0 and C1 without doing an if. Here we go in the buffer. We're going to seek to the end. We're going to read the entire... seek to the back to the beginning. Read the entire file. We're going to go ahead and set that null, again, just so we don't overread the buffer. Then we're going to go ahead and say the first line starts here. We start looping through every time we check to see if we've got any end of lines. If we didn't, we just keep going. Once we get to an end of line, we see whether or not the line was blank. If the line wasn't blank, we're going to go ahead and allocate our link. We come through here, we check to see whether we've got a first free link. In this case, we don't. It's the first time through. We're going to check those links per pool. We already checked this allocation. We're going to go back here, add it to the first free list. Then in here, when we pull one off, we got to set that next pointer to 0. Now I'm going to take a look and make sure that this is initialized 0. And you know what? We could even initialize that string to 0 just for extra added protection. And that does seem like a good idea. I'm going to go ahead and add that in there. We don't need that in this particular case, but I think it would be good to make sure we don't return something that looks like it's got a fake string in it. So I'm going to go ahead and set that line count to 0 so that everyone knows there's no string there. That seems good to me. Now another thing I think we would probably want to check here as we're going through when we do those mallocs, we also probably want to make sure, just as we double check everything in here, that those strings, when they're coming back, we could probably check these appends here to make sure we're appending properly. But what I'd like to do is say, you know what, let's set this to a really low number just to make sure that these things string properly as well. Suppose I set that to 2, does everything explode? Again, I want to see if I can call this repeatedly and have it actually work. Looks like everything's fine, so we're good to go. Alright, that ends our workout number 1. Hopefully that gave you something to think about. Again, there's more things we could do here. Maybe on the next episode of Codelesthenics, we'll go ahead and put these into a hash table so we can look them up more quickly. Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. Let's go ahead and take a look. We were doing lighting last weekend,